Let's continue what I actually started in my previous session, previous class, but I could not complete. That is L Hospital's rule. Okay, and first of all, I am going to write the rules. First of all, the rule one. The rule one is let minus infinity less than or equal to a less than b less than or equal to infinity, and let f and g be differentiable on AB, be differentiable on AB, open interval AB, such that g dash x is not equal to 0 for all x belongs to AB, open interval AB. Suppose that limit x tends to a, fx is equal to 0, which is equal to limit x tends to a gx. Okay, and in that case, number one condition is if limit x tends to a plus f dash x by g dash x is equal to L belonging to R, then limit x tends to a plus fx by gx, that will be also equal to capital L. And number two condition is if limit x tends to a plus f dash x by g dash x is equal to L belongs to minus infinity and infinity, then limit x tends to a plus fx by gx is equal to capital L. So this is the theorem which is actually used to calculate to calculate the limits of indeterminate forms. Okay, so this result is very important, and as I told you in my last class that not only we only do sums, we used to do sums only, but if we want to do it properly, then we have to check the criteria and the conditions also. Okay, and this is rule number one. So you have to, and one thing you have to check it out that here, as I have written that limit x tends to a plus f dash x by g dash x equal to capital L, this capital L can be any real number. So I have written it is belonging to R, but here I have written that capital L is either minus infinity or plus infinity. So these two things are different actually. Although in both the cases the results hold, but here the meaning of the two is actually different. If I write open interval minus infinity plus infinity, that could have been the same as R, but here I have written the set containing two abstract quantities. One is minus infinity, another is plus infinity. So you have to be very careful what I have written. And to start with, these two functions f and g has to be differentiable on the open interval AB, and g dash x should not be equal to 0. If f and g, these two functions, are not differentiable on open interval AB, then L'Hospital's rule will not be applicable to the problems. Okay, so let's start a problem. Let's do a problem. I'm moving on to the next page. The problem is exercise limit x tends to 0 plus log of x plus 1 by sine x, and the corresponding domain of consideration is 0 pi by 2. Now you see that when we actually, I know very well that you can solve this problem quickly, but first of all, you have to analyze. One more thing that I must tell you, that although I am writing here a plus, but these results are also applicable to a minus. Okay, so whether you consider the right hand limit or left hand limit, that doesn't actually change the result. So in the book, they actually considered a plus, but in one of the paragraphs you will find they have mentioned the same logic, same sequence of logic can also be developed for x tending to a minus. So, so I'm taking this particular problem to start with. Now, first of all, how to write the answer, that is very important. So you will write that let fx is equal to log x plus 1, and gx, that is equal to sine of x. Okay, both of these functions both of these functions are differentiable. Both of these functions are differentiable in the open interval 0 to pi by 2. And here you see, if we consider x equal to 0, you cannot consider x equal to 0 because the domain of this is not including 0, because if it includes 0, then sine 0 will be undefined, and sine 0 will be 0 and the thing will be undefined. And you see, if you consider 0, then in that case, if you consider this domain 0 and pi by 2, what will happen, that if you write 0, then log 1 will be 0 and sine 0 will be 0, so that will be indeterminate form, that is 0 by 0 form. So differentiability has to be checked in the open interval 0 pi by 2 for any x, in 0 pi by 2, g dash x gx is not equal to 0, as sine x is not equal to 0. Okay, gx is not equal to 0 and sine x is not equal to 0, as well as, and consequently g dash x is also not equal to 0, and g dash x is also not equal to 0 in 0 pi by 2. Okay, so since we can write that since the functions fx and gx are differentiable at 0, while g dash x is equal to cos x and g dash 0 equal to cos 0, which is equal to 1, not equal to 0. I'm checking the second criteria which is given over here, that is g dash is not equal to 0 for all x belongs to a. Okay, for all x belonging to this open interval ab, and it is not true, and g dash x is not also 0 for other x in the open interval 0 to pi by 2. Okay, so what can we write? We can apply the result that limit x tends to 0 plus log x plus 1 by sine x. This should be equal to, this can be written as f dash x by g dash x. This should be taken at x equal to 0 and this should be taken at x equal to 0, and that is 1 by x plus 1 at x equal to 0 and cos x at x equal to 0, which is equal to 1 by 1, that is 1. Actually, we do not do the analysis part. We do not do the analysis part in the problem while writing the problem, but you have to keep in mind that the results are actually important, because if the functions are not differentiable, what I mean to say that if the functions are not differentiable in any point inside the open interval 0 pi by 2, then this particular result cannot be used. Okay, that is the important thing. Anyways, you know El Hospital's rule. I am going to write my second problem. The second problem is actually important. If phi a, phi dash a, then phi double dash a, in this way, phi n minus 1th derivative of a and psi a, psi dash a, psi double dash a, and psi n minus 1th derivative of a are all zero, and nth derivative of psi at the point a is not equal to 0, then limit x tends to a phi x by psi x, this is equal to limit x tends to a phi nx by psi nx. This is the result which we actually use to solve indeterminate forms problems. Okay, so this result which I am going to prove right now, and you will get to see that there is a connection between the mean value theorem and this particular result. This particular result is actually very important. So how to solve this result? So let us put x is equal to a plus h, so that when x tends to a, then h tends to 0. Okay, now by Taylor's theorem, we have already done the problem of Taylor's theorem. Phi of a plus h is equal to phi of a plus h phi dash a plus h square by 2 factorial phi double dash a plus dot 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 plus h to the power n minus 1 by n minus 1 factorial phi n minus 1 a plus h to the power n by n factorial phi n a plus theta 1 h, where theta 1 is a number lying between 0 and 1. You already know this result. Similarly, but we know that all these derivatives, phi a, phi dash a, phi double dash a, phi n minus a, all these derivatives are 0 actually. All the derivatives less than n are all 0. So from this particular condition, we can get from this Taylor's theorem that phi of a plus h is actually h to the power n by n factorial nth derivative of phi of a plus at the point a plus theta 1h, where theta lying between 0 and 1. And similarly, if you expand psi of a plus h, okay, so with a similar logic, you can get psi of a plus h would be h to the power n by n factorial psi n a plus some other number theta 2 into h, where theta 2 is also a number lying between 0 and 1. Okay, I'm not showing it. This thing is coming because if you expand psi of a plus h with respect to all the derivatives of psi, and we'll see that psi a, psi dash a, psi double dash a, psi n minus 1 a, they are all 0. So only thing we'll be left with is this. Okay, now I'm going to calculate the ratio. So I'm going moving on to the next page. Probably you have copied it. So I'm moving on to the next page. The next page I'm writing, therefore limit x tends to a phi x by psi x, this is same as limit h tends to 0, because I told you that we are putting x equal to a plus h, so that when x tends to a, h is tending to 0. So we get h to the power n phi n a plus theta 1 h, and that is equal to h to the power n psi n a plus theta 2 h. And if I, that this h to the power n and this h to the power n will cancel each other. Okay, and we are going to put the value of h, and we'll get phi n a by psi n a, provided, this part is very important, provided phi n x and psi n x are continuous at x equal to a. This will not be applicable, this will not be applicable to any discontinuity. Okay, so this is the result. Actually, probably you have learned L Hospital's rule in while preparing for competitive examination, but probably I think that in competitive examination, the connection between L Hospital's rule and the Taylor series wasn't shown to you. I don't know, but this is the connection. This is the result which we actually use in the problems. Okay, so let us take another problem. Evaluate limit x tends to 0 e to the power x minus e to the power minus x 2x and x sine x. Okay, first of all, we'll see we'll what how to write it. First of all, we'll write let fx is equal to e to the power x minus e to the power minus x minus twice x, and gx is equal to x minus sine x. And you will see that if I put x equal to 0 over here, x to the power 0, x equal to 0 over there, on the numerator we will get 0, and in the denominator we will also get 0, so that f fx by gx is indeterminate when x tends to 0. Okay, and so therefore, and we cannot find the limit, and we have to take into consideration of L Hospital's rule. Now this function is the exponential. Fx consists of what? It's actually, this type of function is actually called transcendental function. What function they are called? They are called transcendental function. Why? Because it is the mixture of exponential function and polynomial function. Okay, so it is a transcendental function, and this is also kind of a transcendental function. It's a combination of polynomial and a trigonometric function. But you see that each term of this function, they are actually differentiable. Each term of the function is differentiable. Okay, here x is actually belonging to, the domain is not mentioned over here, but here, since the domain is not mentioned, we shall consider x belonging to R. The function, if you write x belonging to R, then in that particular case, what is wrong, you see, uh, in the real line R, the 0 point is there, but in the 0 point, the function is not defined. Actually, the thing is not actually defined. So we have to be very specific for this. So we can write the domain in this particular manner. And we can say these functions are actually differentiable in this particular domain. This function is differentiable in the domain. So we can apply this, and if I do not consider 0, then g dash x is also not equal to 0. So the conditions of L'Hospital's rule are applicable, and we can write it as, by using this, we can write it as limit x tends to 0, e to the power x minus e to the power minus x minus twice x by x minus sine x. Now I'm going to apply this result. So we can write it as limit x tends to 0. This will be to the power x, and that will be minus e to the power minus x, and this is minus 2 by 1 minus cos x. Okay. This form is also, you see, a 0 by 0 form. This form is also a 0 by 0 form. Why? Because if you put 0 over here, you will get cos 0, which is 1, and 1 minus 1 will be 0. And here also you are going to get the same thing. You will get 1 over here, and plus 1 over there. So 1 plus 1, that is 2, 2 minus 2, that is 0. So again we can apply the derivative because it is differentiable, further differentiable. So we can write it as, let us write it as e to the power x, e to the power minus x minus 2 and 1 minus cos x. So in the next phase, we can we can further take the derivative, and we can e to the power minus x, and this will be cos x, uh, sin x actually, minus sin x, minus sin x. This form is also 0 by 0, and if I take derivative once again, you will get this thing. This will be cos x. No, this will be minus sin x. So that would be, uh, because minus sign is there. So cos x derivative is minus sin x. So minus minus will be plus. So we'll get plus sin x, and that would be plus cos x. Okay. And now you see that if I substitute x equal to 0 over there, you will find that it is no longer of 0 by 0 form. So we can write e to the power 0 plus e to the power minus 0 by cos of 0, and that would be equal to 1 plus 1 by 1, that is 2. That is your answer. Okay, so the main logic is you can apply the derivative as long as the derivative, the function is derivable, the derivative can be taken. But if the function is not differentiable in the interval, then this L'Hospital's rule cannot be applied. Okay, that is the important part. One more problem that we can do is, limit x tends to 0, 10x minus x by x cube, where the domain of consideration is taken to be 0 pi by 2. Okay, so here also you can do the same thing. Take fx equal to 10x minus x, and gx is equal to x cube. They are defined in 0 pi by 2. Okay, Now also fx and gx are differentiable for the points for x belonging to 0 pi by 2, open interval 0 pi by 2, and g dash x is equal to 3x squared, so that g dash 0 is equal to 0. Now the problem is that, you see here, g dash, what was my condition in the previous stage? My condition was that I wrote in the very first uh, page, that g dash should not be equal to 0. G dash must be non-zero. But here we are getting, that g dash x is actually is 0 at x equal to 0. That means g dash x is equal to 0 at x equal to 0. We are getting this. So probably this implies that, the if you take one derivative, then I mean, if I write that, I mean to say that if I write limit x tends to a fx by gx, that is the thing. Okay, so I can write it as limit x tends to 0, 10x minus x by x cube. That was the indeterminate form. And if I take the derivative, so we'll get sec squared x minus 1 by 3x squared. That is also indeterminate form, because the derivative, the gx function is actually 0 at x equal to g dash x is 0 at x equal to 0. So that is also 0 by 0 form. So we can take the help of this result, the second result which I proved over here, this result, and we can keep on differentiating the item as long as the derivative is not 0 in the denominator. So we shall write it as limit x tends to 0, 2 sec x and sec x 10x, and we can write it as 6x. That is also what, it is also, if I put x equal to 0, the denominator will become 0. So we cannot, we this is also indeterminate form. Okay, because 10 0 is there, 0 is there, so it's 0 by 0. But we can cancel 2 and 6, we can write it 1/3, and we can take the derivative further. So we can write it as sec square x 2 sec squared x 10x by x, and you take the derivative. So we write 1/3 limit x tends to 0, and we can write 2 sec x 10 squared x, and that can be written as sec squared x into sec squared x by 3. And if we put x equal to 0 now, you will get not 3 has already been taken into consideration, that would be 1, that is 1, and therefore the ultimate result will be 3. This result will be 3. We are going